This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. In this section, I'm going to be talking about temporary objects, where a temporary object is a type of object introduced by the compiler that doesn't explicitly appear in the code itself. At this point, I'd like to discuss temporary objects. So what exactly is a temporary object? A temporary object is an unnamed object that's introduced by the compiler. In other words, it's not an object that's explicitly part of your code, but something that the compiler actually introduces. And temporary objects can appear in a number of different circumstances. One is in the evaluation of expressions. One is in the passing of arguments to functions. Another is in returning values from functions where the return type of the value that's being returned is a non-reference type. And another situation is reference initialization. And you might wonder, well, why do we need to worry about temporary objects? Because the compiler is taking care of them for us, because this is sort of implicit in the notion of what a temporary object is. The reason that we have to worry about temporary objects is because they can have an impact on performance. So I'll give a few examples of situations in which temporary objects can arise. One is in the evaluation of expressions. So for example, we have some code here that's making use of the string class in the standard library. We create a few string variables s1, s2, and s. And then we're going to use the addition operation to concatenate one string to another. And when we do this, the concatenated value, in other words s1 with s2 concatenated to it, is going to be assigned to s. But before this assignment operation can take place, there needs to be something on the right-hand side, which is a variable that can be assigned to s. But s1 plus s2 itself is an expression. It's not actually an object that can be assigned to s. So what the compiler will do is it will automatically generate a temporary object to hold the result of s1 plus s2. In other words, the result of the operator plus function that's basically responsible for doing string concatenation for the string class. And it will generate code which looks sort of something like this. It will generate a temporary object, which I've called _temp. The actual temporary object generated by the compiler has no name, but just for illustrative purposes, I'm calling it _temp. And it's initialized to be s1 plus s2, in other words, the result of adding these two strings, in other words, performing a string concatenation operation. And then this temporary object is assigned to s. Another example where temporary objects can appear is during passing of arguments to functions. So in this case, we have a function called func. It takes a reference to a constant double as a parameter, and then returns a double. And then here we're trying to invoke this function by passing it a value of 3, which is a literal of type int. And when the function func is invoked, because this reference here, this reference parameter, has type double, or it's a reference to a double, or more specifically a const double, this reference has to be bound to something that is of type double. But 3, this value 3 here, it's of type int. So the reference for this function func cannot be bound to the value 3. So instead what the compiler needs to do is it generates a temporary object of type double, which I've denoted by _temp here. Again, the temporary object doesn't actually have a name, but I'm calling it _temp just for illustrative purposes. And then this variable, which is of type double, is initialized to 3. So this int value of 3 is converted to a corresponding double value, in other words 3.0. And then this temporary object is passed to the function func. And this reference here is going to refer to this temporary object. Another situation in which temporary objects can arise is during reference initialization. So I have a code example to help illustrate this. We have a variable I of type int, which is initialized to 2. And then on the next line, we have a reference. And this reference is particularly a reference to a const double. And we're trying to initialize this reference d to be bound to I. In order to do this, however, the compiler is going to need to generate a temporary object. The reason why, the important thing to notice here, is that I is not a double. I has type int. So this reference to a double can't refer to I because I is not a double. So what the compiler will do is it will create a temporary object, which I've denoted by _temp here, and initialize its value to I. So the value of 2 that's stored in I is going to be propagated into this variable, except it will now become a double value. And then it will take the reference D and it will bind it to this temporary object. Another example of a situation where temporary objects can arise, and this is actually a very, very common one, is in returns from functions, function returns. In particular, in cases where the function doesn't return a reference type. So in this code example, to illustrate this, we have a function called getMessage, which returns a string from the standard library, a string type. Notice it's not a reference type. Then we have some code here where we have a string variable called s, and we call this function getMessage, and then the return value from this function, which is a string, is then assigned to the variable s. In order to execute this line of code here, the compiler needs to introduce a temporary object. The reason why is that it needs to store somewhere the return value of this function. So the return value of this function can then be passed into the assignment operator, in other words, operator equals, for the class string to actually do the assignment part of this line of the code. So in effect, this line of code here gets translated into the 2 lines that appear in the comments below. The compiler will generate a temporary object, which I'm denoting by _temp. It will then initialize this temporary object with the return value from the getMessage function. And then this temporary object will be used for the assignment operator to assign to s. As far as temporary objects go, their lifetime is usually the full expression that contains the point where the temporary object was created. So for example, the temporary object that's generated on this line of code here that stores the return value from getMessage, it reaches the end of its lifetime at the end of this statement. So after this line of code, the variable would be destroyed. This is the most common case. There are a few exceptions where the lifetime can be longer, but this is the most common situation. On this slide, we have a simple complex number type, in particular the class called complex. We have a few constructors and assignment operators and a destructor, and it has a member function for getting the real part and a member function for getting the imaginary part of the complex number. And in addition, it overloads operator plus to add 2 complex numbers, and then the return value is another complex number. And what I want to consider is for this little program below, main, which is making use of this complex number class, what sort of temporary objects are involved with the particular code that's being executed by the main function. So this is what we're going to consider in more detail in the subsequent slide. So now I'd like to consider the code example from the previous slide in more detail. And in particular, I want to focus on temporary objects. So the main function in the code example from the previous slide looked like what's shown here. And assuming that the compiler doesn't perform any optimizations, this code is effectively going to be translated into what's shown here by the compiler. And in effect, the compiler is going to be introducing 2 temporary objects, the one that I've denoted by _tmp1 and the one that I've denoted by _tmp2. So in the case of _tmp1, the reason that this temporary object is needed, it comes from this line here in the original code. Here we're trying to construct b from the result of adding a to a. So we have a plus a. This is adding 2 complex numbers. It's the addition operation is going to return another complex number, but that returned value has to be saved somewhere so that it can then be passed to the constructor, which initializes b. So in order to save this value that's returned by a plus a, we need a temporary object. So this is why the compiler generates this first temporary object. It stores the result of a plus a. The second temporary object, the one I've denoted by _tmp2, this is necessitated by the a plus b operation in this expression on this line here. When we add a plus b, we have to save the result that's returned so that that return value can then be used to assign to b. So in effect, what's going to happen is the compiler is going to take the return value from a plus b and use it to initialize a new temporary object. And then this temporary object, _tmp2, is then going to be used to initialize b by assignment. If we look down below, we also have the operator plus function, which looks something like this on the previous slide. This code here is going to get translated by the compiler into the code that's shown at the very bottom of the slide. In particular, one temporary object is going to be introduced associated with _tmp. And essentially, that comes from this line here, where we're saying we're creating a complex object by initializing it to have a certain real part and a certain imaginary part. But this value has to be saved somewhere so that it can be returned. So the compiler will create a temporary object to hold this constructed value, this complex number, and then the returned value that gets returned is this temporary object. In C++, there's both a prefix and postfix version of the increment and decrement operators. And what I want to illustrate by way of the code example on this slide is that often it's more efficient to use the prefix version of the increment and decrement operators rather than the postfix version. And we'll see the reason why as we go through this example. And partly it relates to temporary objects, although not entirely. So if we look at this class that we have on the slide, we have a class called counter that is a single data member called count underscore of type int, which is just the value for the counter. So this type just represents some kind of counter type. We have a default constructor which initializes the count to 0, a function called getCount which allows us to return the current count value for the counter. And then we have two versions of operator plus plus, the prefix increment operator and the postfix increment operator. And down below we have some code in this function main which is using this counter class. So we create a counter called x, a counter called y, and then what we're going to do is we're going to apply the prefix increment and the postfix increment operators and consider what's the complexity of these operations, what things are involved. So if we look at the first line here where we're saying plus plus x, well plus plus x is the prefix increment operation, so it's going to invoke this function here. And what this is going to do, this is going to increment the value of the counter data member, this count data member here, and then return a reference, because of the ampersand here, it's going to return a reference to this. In other words, the object that we're operating on. So in total, basically the only operations we're doing is we're incrementing a single integer. And then we're taking the result and we're going to assign the result to y. So the cost of this line of code here is an integer increment plus an assignment operation. If we go on to the next line here, the cost, as it turns out, is much higher. This is going to invoke the postfix increment operator, which is this function here. If we look inside this function, the very first thing we have to do is we have to save the current version of the counter, because the convention that's followed by postfix increment is that normally it will return the value before the increment operation takes place. In other words, it returns the old value before you increment. This implies you have to save the old value. So we're saving the old value here by creating a new counter object and saving the object we're operating on into this variable old. Then we increment the count, and then we return the old value. But the story doesn't end here, because in this case the value we're returning is not by reference, it's returning by value. So the value we're returning has to be copied into a temporary object which holds the return value of x++, and then the return value is then that's stored in the temporary object is then used for the assignment operation to assign the value to y. So in total what we have in executing this line of code here is we have to create one temporary object, which is caused by the fact we're returning by value. We have one named object due to the fact we have to save the old value so that we can return it from this function. Each of these, the temporary object and name object, need to be constructed and destroyed. So we have two constructor calls, two destructor calls, and then we have an integer increment operation plus the assignment operation. So if we compare these two lines of code, line 21 and line 22, line 21 is much lighter weight. Line 22 has all the same computation as line 21, plus it has to create and destroy a temporary variable, a named variable, which involves calling two constructors and two destructors. So this is the reason why we want to take temporary objects into account, because they can influence the complexity of code.